So in this video, I'll discuss how to determine the amount of energy that is needed for a phase transition to occur. So with this video, I'm going to utilize a heating curve. And recall, the heating curve just gives you an example or an illustration of the heat that is added and how it affects the temperature. With the heating curve, we can see the different physical states as well as the transition between those physical states where each of those occur. And so here we have our heating curve. It's labeled A, B, C, D, and E, and we can identify what each area represents. So what is labeled as A represents our solid. I'm just going to write S for solid. And so anything at that point is in the solid phase, but as heat is added, the temperature will increase. The temperature increases, and then you reach that plateau, which is shown as B. And so at that point, this is where your phase transition takes place. So here we have a phase transition where our solid is being converted to liquid. And so in order for the solid to be converted to liquid, we call that melting, but it's also referred to as fusion. And so in order to determine the amount of energy associated with that change, we have to think about our heat of fusion. That heat of fusion tells you the amount of energy needed in order for all of your solid particles to be converted to liquid. From there, we get to part C, so it's labeled as C. And so with part C, this represents our liquid, so I'll just write an L. And so at that point, as the heat is being added, the temperature continues to increase. And then again, you're going to reach another plateau. Everywhere you see a plateau represents a phase transition. So what is labeled as D represents the process in which the liquid is converted to a gas phase, which is known as vaporization. And so the amount of energy needed for all of the liquid to be converted to gas is known as the heat of vaporization. Once all that liquid is converted to gas, then you reach the gas phase for this substance. So I'll just label that as G. And so the key thing with determining the amount of energy needed for a phase transition is to understand what phase the particle or the substance is in initially. And based on the temperature and the amount of heat being added, we can then determine what phase it ends up in, and then determine the energy associated with each phase in order to determine our phase transition total energy. And so again, we start with the solid. You may not always start with that. Again, you're going to have to look at what temperatures are being provided. But based on how this heating curve is labeled, you have your solid phase, and then you reach the point where you have to utilize your heat of fusion in order to melt all of the solid and convert it to liquid. And then as heat is added, you get to the point where all of your liquid is then being converted to the gas phase, and that utilizes your heat of vaporization. And once all of it is converted to the gas phase, those particles are then in the gas phase. And so for a phase transition, the transition has a certain amount of energy. But if we're looking at changes within the phase, we can think about our energy for heat, or from our equation for heat, which is calculated as the mass times the specific heat times the change in temperature. That change in temperature we can show as delta T. T final minus T initial. So the specific heat simply tells us the amount of energy needed to raise 1 gram of a substance by 1 degree Celsius. And so as we're heating those solids, as we're heating the liquids, and as we're heating the gas phase particles, this requires the heat equation, which is based on the amount of the substance, how the temperature changes, as well as the specific heat for that substance. And so if we work an example and apply this, have the example, how much heat is required to raise the temperature of 250 grams of water from 34.5 degrees Celsius to 89.7 degrees Celsius. And so what do you want to do when you're given a temperature? You want to think about where it's starting at and where it ends up at, because that will dictate how many equations you have to use to calculate heat for different areas within the different phases, or whether or not we're in a single phase, whether or not we're transitioning between 1, 2, or 3 phases, but that temperature is important. So if we think about our heating curve and the fact that we're dealing with water, now I don't have numbers on here, but we know that water, the freezing point for water, which would also be the melting point for water, is 0 degrees Celsius. So I can imagine that this temperature is 0 degrees. We know that the boiling point is 100 degrees Celsius. So I can use these numbers. And so because my starting temperature, so my initial temperature is 34.5, my final temperature is 89.7, I know I'm starting somewhere in here and I'm ending up somewhere in here. So I don't have to worry about going from the solid to the liquid or from the liquid to the gas. I'm simply looking at how much energy it takes for me to raise the temperature of this liquid, but it's still going to remain a liquid. And so once you know whether or not phase transitions take place, you know which equations you have to use. Again, if we're dealing with the transition involving melting or fusion, we have to think about the heat of fusion, and that tells us how much energy based on the mass. So we simply multiply our mass by the heat of fusion. Same thing with the heat of vaporization. So if we have to overcome the conversion from the liquid to the gas phase, then we have to use that. But in this case, we don't have that. We're simply within this one phase. So we're within this one physical state. And so that means that we have to use the equation of heat being equal to the mass times the specific heat times the change in temperature. And so again, by looking at what your temperature, initial and final, what those values are, we can determine which process we have to utilize. And so if we take this problem and actually work it into the equation, the problem gave us the mass, which was 250 grams. We had our initial temperature, which was 34.5 degrees Celsius. We had our final temperature, which was 89.7 degrees Celsius. So again, our equation is heat is equal to mass times the specific heat times the change in temperature. So we have our mass, which was 250 grams. The specific heat of different substances vary, and they also vary based on the phase in which that substance is present. And so here, because we're dealing with water, and we know that 34.5 degrees Celsius to 89.9 degrees Celsius represents the liquid phase. And so the constant value for the specific heat of water in the liquid phase is 1.00 calories per gram. So that's per gram degrees Celsius. So that's a constant value. So for my specific heat, I have 1.00 calories per gram degrees Celsius. And then delta T, we were given the initial and the final. To figure out delta T, it's just the final minus the initial. So the 89.7 degrees Celsius minus 34.5 degrees Celsius. So when you get that difference, it's going to be 55.2 degrees Celsius. And so that's your delta T. Delta T just tells you the difference between your final and your initial. And so now, based on the fact that we were within one phase, we're not involving transitioning to a different phase, we're simply using this equation, mass times the specific heat times the change of temperature. Once you put that in your calculator, it would give you 13,800, and my units are going to be calories. So if I look, I have gram in my numerator divided by a gram, so they cancel. Degrees Celsius divided by degrees Celsius, so they cancel. So I'm simply left with calories. So the amount of heat needed to raise the temperature of 250 grams of water from 34.5 degrees Celsius to 89.7 degrees Celsius is 13,800 calories. Okay, so we'll try another one. So here, again, we're asked how much heat is required to raise the temperature of 175 grams of water from -8 degrees Celsius to 107 degrees Celsius. So again, you want to think about what the temperatures mean and how it impacts the physical state in which the water will now be present. And so if we're dealing with a temperature of -8, again, I can put in numbers on this chart. I can just say that this represents 0 degrees, so where my B is located at, that's my freezing point. Where my D is located at, so I can't draw straight, but where my D is located at represents the boiling point, so that's going to be 100 degrees Celsius. And so that will allow me to know exactly what transitions are taking place, if any. And so because this problem tells us that we're starting at -8, so we're somewhere down here, and we're going all the way up to 107, that means we're somewhere up here. So by looking at where you're starting at and where you're ending up at, that lets you know which process has to take place or how many have to take place. And so in order to go from a -8 to 107 degrees Celsius, that means that we're starting at the solid phase. We have to heat up, and then we have to overcome the fusion. We have to overcome that melting. Then we move up to the liquid phase, and that keeps heating, but then we have to overcome the vaporization so that all that liquid is converted to gas, and then we actually have to heat up while in the gas phase. So that means that we're dealing with something in each segment that was listed on this heating curve. So we're dealing with 5 different segments involved in the increase of the temperature for this 175 grams of water from a -8 degrees Celsius to 107. And so we have to think about what each piece means. Again, when you're within a single phase, so whether we're talking about the solid phase, the liquid phase, or the gas phase, anytime you're within a single phase, you have to use your heat equation. So mass times specific heat times the change in temperature. Anytime you're dealing with transitions, if you're transitioning from the solid to the liquid phase, that means that we have to overcome our fusion. And so we can call that heat of fusion. So you can see it as a Q, you can see it as a capital H. I'm just going to use Q for this, heat of fusion. So that means that we have to multiply our mass times the heat of fusion. And then once we get to the liquid, it's going to heat up. We go back to that first equation. And then in order to go from the liquid to the gas phase, we have to undergo vaporization. And so again, by looking at the temperatures, we can then identify what equations need to be used. So for part A only, I'm going to label these equations as 1, 2, and 3. So for part A only, so that as we're heating up the solid, we're going to use equation 1. But then we get to the point in which we reach that first plateau, which represented, well, I'll go back so you can see the curve as I'm discussing it. So for part A, we're going to use that first equation, which was just the heat is equal to the mass times specific heat times change in temperature. And then in order for the solid to be melted, we have to undergo the fusion. So you'll see your second equation, your mass times your heat of fusion. And then that means that our solid has been transitioned or transformed into liquid. And from there, our liquid begins to heat up. And so it heats up from 0 all the way up to 100 degrees using that first equation because we're within that one phase. But then in order to get up to 107, we have to actually vaporize all of the liquid. So it has to be converted to the gas phase. So we have to overcome that plateau by using equation 3 in order for the particles to be converted to the gas phase. And from there, because the gas phase starts at 100 degrees Celsius, but we're ending up at 107, That means that we have to actually heat up within that phase. And so in order to determine the total amount of energy or heat that is needed to go from -8 to 107, we're going to have to figure out these individual pieces, how much energy it takes for the solid to heat up, how much energy it takes for the solid to melt completely, how much energy it takes for the liquid to heat up, how much energy it takes for the liquid to vaporize completely, and then how much energy does it take for the gas to heat up. So we have to do those 5 segments because based on these temperatures, we're involved in each segment of the heating curve. So we have to take these 5 equations and then total them at the end. So if we take each one, so I'm going to just keep the same labels as A. So with A for our heat, it was our mass, 175 grams. Our specific heat, again, we have to look at the fact that we're dealing with water that is now in the solid phase at -8 degrees Celsius, and it has a different specific heat. The specific heat of solid water is 0.490 calories per gram degrees Celsius. So although the equation is the same, we have to make sure we use the correct specific heat value. And then our change in temperature. So here, even though we're going from -8 to 107, the change that we're talking about is just what does it take to get us to the point in which this solid gets or reaches the melting point. So we're really going from -8 to 0 in order for this melting process to start. So if I go back to that heating curve again, if we're starting here and I just put an estimated line here, in order to get to B, we have to go up to this point, which is our 0 degrees. So for that first equation, when we're talking about our change in temperature, we're really saying how much does it take to go from -8 to 0. So our delta T would be 0 degrees Celsius minus a -8 degrees Celsius, which is simply 8 degrees Celsius. And so once you put this in your calculator, your 175 times your 0.49 times your 8, and it becomes positive, because remember, if you subtract your negative, it becomes positive. That gives us 686 calories. Again, if we look at our units, we have a gram over a gram, degrees Celsius over degrees Celsius, leaving us with calories. So that's how much heat it takes to simply increase the temperature from -8 to 0 degrees Celsius. At that point, it then begins the melting process. So remember with this equation for our heat, it was our mass, 175 grams. But now we have to multiply that by the heat of fusion in order for the solid to be converted to liquid. The heat of fusion for water is 79.5 calories per gram. So we're now just multiplying that mass, the 175 times the 79.5. And once you do that, it gives you 13,912.5. So that's how many calories we have there. Again, our units cancel because we have a gram divided by a gram. So this is how much energy it takes to simply melt all of this water. If we were to add the 2 values that we already have, then we would actually have the amount of energy it needs to completely melt 175 grams of this water that began at -8 but ended up at, in this case, if we stopped, it would be 0. But that's not what the problem asked us. The problem asked us to go from -8 to 107. So now that the water has melted, the liquid water is present, and it will begin to heat up. It's going to heat all the way up, so all 175 grams are now going to heat. The specific heat of water, since we're now in the liquid phase, is 1.00 calories per gram degrees Celsius. And this water is going to remain in the liquid phase until it reaches the boiling point, or the point of vaporization, which is 100 degrees Celsius. So that means that our change now in temperature is 100 degrees Celsius minus 0 degrees Celsius, which gives us a delta T of 0. I'll just go ahead and write that extra step out. So 100 degrees Celsius minus 0. Because remember, once the fusion took place, we were then in the liquid phase. And so we're trying to get to 107, but once we reach 100, we're at the point in which it's going to start vaporizing. So we're only in the liquid phase from 0 degrees Celsius to 100 degrees Celsius. And so that's why these are the values being used for the delta T. And so once you have that, again, you're going to multiply your mass times your specific heat times the change in temperature. When you do that, you're going to get 17,500 calories. So what that means is that in order to heat up 175 grams of water, it's going to take 17,500 calories. Because once we reach 100 degrees, we're now at the point of vaporization. So now we're at the point in which this liquid is ready to be converted to gas. So we can use equation 3 now. We still have that same mass, 175 grams, because that's our sample size. But now we've reached a point of vaporization. So now we have to use the heat of vaporization. And the heat of vaporization is 539 calories per gram. These values and constants that I'm calling out, these are things that will be shared with you. So you're not expected to go through and try to memorize these. The different specific heat values, as well as the heat of fusion and heat of vaporization, will be provided, but you have to know when to use which value. So you have to know based on the temperature which specific heat. You'll be told whether or not it's solid, liquid, or gas. And you have to know based on the phase transition whether or not you're dealing with the heat of fusion or the heat of vaporization. But here, with the heat of vaporization based on this mass, when you multiply those two values, you're going to get 94,325 calories. And so what this tells us is that it takes 94,325 calories in order to completely convert your liquid to the gas phase. Once we've converted all the liquid to the gas phase, then now the particles in the gas phase will heat up. Same mass. So once you know the mass of your sample, that's going to be the mass for all of those equations. But now, because we're looking at heating this one phase, we're not looking at transitioning into a different phase. We're looking at heating this one phase. So we have our mass times our specific heat. The specific heat of water in the gas phase is 0.497 calories per gram degree Celsius. And then our change in temperature. Again, in order to enter the gas phase, we were at 100 degrees Celsius, but the problem asked us for the final temperature to be 107. So that's going to be our final temperature, 107 degrees Celsius. Our initial temperature is going to be 100 degrees Celsius. The key thing is remembering that because we're dealing with different transitions, even though the problem started at -8, your change in temperature is based on which phase you're in. We can't have a change of 107 minus -8, even though that is technically the overall change in temperature. But we have to think about the different phases, and because there's different energy and heat associated with each phase, we have to consider which phase we're in. So here, we're only talking about the heat, the amount of energy needed to raise the temperature of this gas. We entered the gas phase at 100 degrees, but the problem asked us for the final temperature to be 107, so that's why our delta T is simply 107 degrees Celsius minus 100 degrees Celsius. So once you multiply all of that, you'll end up with 608.825 calories. And so what this value tells you is that based on 175 grams of water, it's going to take 608.825 calories in order to raise the temperature of water in the gas phase up to 107. So now you have the energy associated with each phase from our heating curve. In order to determine the total energy, you're now simply adding those values together. So if I do the heating curve, we look at A, that was our heat for the solid. Based on our calculation, that value or that amount of energy was 686. If we looked at B, that was for the transition from the solid to the gas. That value was 13,912.5. If we look at C, that was the energy for heating the liquid. That value was 17,500. And if we look at D, the energy associated with transitioning from the liquid to the gas phase, that value is 94,325. And then if we look at E, which was the energy associated with heating the gas, after all the liquid was converted to gas, that value was 608.825. So if we take all 5 of those values and add them together, that gives us 127,032.325 calories. So I can just report that as 127,032 calories. That's how much energy it would take to convert 175 grams of water from -8 degrees Celsius up to 107 degrees Celsius. So I hope this helps. You've now seen 2 different ways in which you can calculate the heat. Some examples or some problems may require that you deal with multiple transitions. I did this one that showed you utilizing all 5 areas of the heating curve. Some may require less than that. We could have done a transition that involved 3 areas. Or as you saw with the first example, it didn't involve any transition. We simply stayed within 1 area of the curve. So the key here is just remembering that depending on what temperature you're starting with and what temperature you're ending up with, that will determine the equations that you will utilize. So you will either, if you're within one phase, you'll use the mass times specific heat times the change in temperature. If you're dealing with the substance melting, you're going to use the mass times your heat of fusion. If you're dealing with the substance boiling or vaporizing, then you're going to use mass times the heat of vaporization. So again, you want to just start by looking at your temperatures and think about what that indicates in terms of the phase that you're starting in and ending up in. And from there, that will tell you how many equations you need to use and which equations to use. And once you utilize the energy for each segment, you simply add them together to get the total amount of energy required for that change. So I hope this helps. If you have any other questions, please let me know. Thank you.